Good morning and good afternoon to everyone. I'm Hakan Tureci from Princeton University. On behalf of the organizing committee, including my colleague Vinod Menon, I want to welcome you all to the symposium on computing with physical systems. I'm delighted that all of you were able to tune in here. So at the outset, let me first thank the initiative for the theoretical sciences at the Graduate Center, CUNY, for making this organization possible. And also, I have to thank Govin Michel and Vadim Oganessian for their help with putting together the symposium. So let's see. We have 6 talks today given by experts. We've been thinking about computing with physical systems, and doing that in an array of physical platforms, including optical, polartonic, electronic, mechanical, FPGAs, and superconducting circuits. Probably there are a few more platforms that we'll hear about, maybe bucket of water, right? The most interesting one. So we'll have also talks covering the fundamentals and foundational ideas in the physics of computing and computing with physical systems. I'm especially looking forward to that. So we asked the speakers to confine their talks to 45 minutes, including questions and discussion. So 30-35 minutes is probably the ideal sweet spot there. And we'll have 30-minute breaks after every 2 talks, and there will be a lunch break around 12. All right, good. So our first speaker is Joni Dambre from University of Ghent in Belgium. So thank you, Joni, for coming over to give us an overview of past 20 years of research in reservoir computing. The stage is yours.
Okay, thank you. So when I accepted this invitation and then I started working on the slides, I suddenly realized that it's already been like since 2017 that I gave the last version of this talk. And there is actually so much to say, so I really had to be very selective. And I took a bit of a historical approach, since our team has been in reservoir computing actually from almost the very beginning of this quite fascinating topic. So what are the origins? Well, the origins are actually 2 people or 2 groups. One of them is Herbert Jaeger, who I'm still collaborating with, who came up with echo state networks at the beginning of this century. So the first publication was 2004, but as you know, with research, the ideas are usually a few years older than the first publications. And the second person is Wolfgang Maas, who came up with liquid state machines, and both of them actually sort of got similar ideas roughly independently at the same time. And actually there were also some other people that we later discovered that there's actually quite a few places where these kinds of ideas have emerged around a similar time. So I've tried to put in references here and there, but not everywhere, because sometimes it's just too many. So what is the core idea of reservoir computing? So basically what you have is a dynamical system, most often a nonlinear dynamical system, that must have 2 properties. One is fading memory, but I will go into that a little bit deeper in a bit. And fundamentally, that just means that if you take away the inputs, then their impact on the dynamical state of the system will fade away slowly through time. And so this is just my picture that I use for people who are not really familiar with this concept. So this is just a first order IC filters and two input signals that are different up to a certain time and then become similar at the black line. And you see that the difference between the single state voltage of this system, that the difference gradually decreases. So the impact of initial conditions gradually disappears. So this is one property, and the other one is the approximation property, which in a non-theoretical way means that the more input time series are different, the more their representations in state space should be different. So if I make two very different signals here, then their representations in this one-dimensional state space obviously are going to be more different. Normally, we're talking, of course, about higher dimensional state space. So these are the two core properties that were originally formulated as the properties that a reservoir should have. Through time, interpretations have been changed a bit, and especially in physical reservoir computing, the approximation property is kind of hard to theoretically prove in most cases. Anyway, so if we go to these two versions, so what Herbert did was a discrete time, basically a random recurrent neural network. So he worked with randomly fully connected recurrent neural networks. All the neurons in this network are driven by an input signal with different scaling factors, also random. And all the neuron states are being observed and then linearly combined in the readout. And the only thing that is optimized in that system is actually the weights of the output here. So just a linear combination, basically, so with linear regression or linear classification. In Wolfgang Maase's system, so Wolfgang is mostly fascinated by trying to decipher the workings of the brain. Actually, he's only fascinated by that, so any practical applications have always been less of interest to him. And so he thought, like, okay, let's come up with a model for cortical columns. So these are spiking neural networks. And what is also different to Herbert's system, that this is a spatial system. So the neurons are organized in a 3D fashion. There exists something like distance between the neurons. Connectivity is distance dependent. So the system is slightly different. But the approach was largely similar. So it's random connectivity based on some connectivity distributions. Inputs are sent into the system, spiking inputs in this case, of course, and outputs are read out and then linearly combined to come up with a target signal. And in both cases, of course, it's like a machine learning type of setup. So you have a desired relation between input sequence and output sequence, and this linear combination has to approximate that. Okay. Let's go on. So going back to these theoretical properties, they have two consequences. First, the fading memory property implies that the system needs to be stable when driven. And that last bit is often forgotten because we are often working actually with systems that are slightly unstable, but that have the property that if you drive them with an input due to the nonlinearity or due to the system's property, the input stabilizes the system. And so they have to be stable when driven. They can be unstable in undriven situations. And the other thing, the approximation property. So anyone who is familiar with concepts in machine learning, basically what this reservoir does is it does a very high dimensional projection of your input time series. And in the machine learning world, you know that if you project your inputs into high dimension, they become easier to separate. It becomes easier to solve tasks on them. So basically what you need is that the states that you observe from the system, that there's many of them, and that they're all ideally different. So they respond to the inputs ideally in many different ways. So that means that most of the time you will want a rich nonlinear dynamical system. Okay, so how does this translate into a recipe? And I'm going to focus on echo state networks now because they are still a very good model system to to reflect about properties of a system and its use as a reservoir. So basically what you do is you initialize a few hundred most of the time neurons with either hyperbolic tangent or sigmoid nonlinearity, most of the time fully connected. You sample your input weights, your node biases, and your internal weights from some distribution, uniform, Gaussian, and then you just send your input time series through the network, collect the neuron states, and then you just do some traditional machine learning model on top of that. So originally that was just linear regression with mean squared error minimization. Nowadays, we're often also using logistic regression, or people have used linear support vector machines, Gaussian processes, or even nonlinear like MLPs on top of reservoir computing. And so all kinds of things have been done there. So that's the basic recipe. But that doesn't mean that this thing that you just randomly initialize is going to be good at solving your task. So the next step is, so how do you tune this reservoir to become good at solving your task? And then we have to dig a little bit deeper into the properties of this reservoir. And so here at the top, you see like the discrete time update equation of an echo state network. So the F is the nonlinear function. So you take a nonlinear function, and in this case, hyperbolic tangent of the state vector of the previous time step with a weight matrix. You add to that an input weight of the input signal, current input signal. Sometimes you do output feedback, and so you feedback the trained output back into the reservoir also with random weights. And there's one that is not mentioned here, that is the bias weight. So normally you also add a constant input to each neuron as well. And these are the four things here, and these are like 4 tuning knobs that you have. And so in machine learning, you would call them hyperparameters, to make the reservoir or any reservoir sampled from the distributions you use more or less suitable for your task. So for example, if you scale the input weights differently, so there's a signal coming into the reservoir here, if you make the input signal scaling larger, you will see that it travels through more of the nonlinear parts of this hyperbolic tangent. So very small input scaling with zero bias typically gives you an almost linear reservoir. In this case, larger input scaling typically gives you a more nonlinear reservoir, but in this case still symmetric. If you add the biases, so the DC inputs to the neurons, and you start scaling those, then you can also offset the whole signal, either in a small signal regime or large signal regime, to a different region of the nonlinearity. So input scaling and bias scaling typically tune the nonlinearity of the ESR. So if you go to physical systems, there will probably also be some parameters that affect the nonlinearity of your system. Then the internal weight scaling, so that's the connections inside a reservoir. So typically if you scale up all the weights, and you're going to increase the gain in the system and the feedback gain in the loops. So at some point you will get wild oscillatory behaviors in this case, because this nonlinearity is saturating, so you get switching behaviors between 0 and 1s. But in general, the weight matrix itself also can cause positive gain loops. You can even get chaotic behavior. So what we typically see there is that for most tasks, it's best if you scale up the weights such that you move close to the edge of stability at the stable side, or slightly beyond, but in such a way that although the weight matrix would make your system unstable, if you drive this system, and then you see that the signals get closer to regions of the nonlinearity with lower gain, so that counteracts the gains that would make the system unstable. And then the last one, it's not in this equation, but sometimes they also add like a low pass filter to the input of the neurons. So it's like a diagonal of the self-connection matrix, which also tunes the time scales a little bit of the reservoir, but I'm not going to go into that at this point. So these are your scaling knobs. You just tune these knobs. Typically, you just do grid search or some other hyperparameter optimization algorithm to find the combination of hyperparameters that make this reservoir best suited for your task. And then if you see, for example, these are sweeps where you sweep like the input scale versus a spectral radius. A spectral radius is like a theoretical approach to scaling the weight matrix close to the edge of stability. For two standard academic stupid benchmark tasks, one is the delayed XOR, so you drive the signal with bit streams and you want to compute the XOR of the last bit and the bit before that. The other task is Norma 10, that's a nonlinear moving average system that you need to approximate. So these are like standard echo state network benchmark tasks. And now the thing is, so you see here sweeps of input scaling versus spectral radius, and you see, so the top plots are without any bias, so no DC input to the neurons. The bottoms ones are with large DC input to the neurons, and you see that these plots look totally different. You also see that for different tasks, the optimum and the big black crosses are in totally different places. So it really is important that you tune these parameters to match the kind of input that your task needs, and of course also the task that you need to solve on these inputs. And so you always need to tune these parameters. For the standard benchmarks, of course, there are typical values that you can find in literature. If you are working with new tasks and new systems, you have to, of course, in the new system, first identify what are the tuning knobs in this system, and then go looking for the right regime for your task. Okay, there's been quite a few theoretical studies in that field, and one of them happens to have been done by myself. So early on, Herbert Jäger defined a metric called linear memory capacity. So capacity here just means a squared correlation coefficient between the desired output of a task and the output of the reservoir after it has been trained. Always seen from a linear regression perspective, so where you minimize mean squared error. The linear memory capacity is just like a series of tasks where you always have to reproduce the input of a certain number of time steps ago. So that's the tau here in the x-axis, and the curves are for different reservoirs, showing how this memory capacity decays if you look back further in the history, because it's fading memory, so at some point this memory capacity has to decay. And then they also look at the sum, so the integral under the curves, to look at the total linear memory capacity. So this is one of the typical things that you first analyze for a new system, be it a physical or a simulated reservoir. And then you see that you can see different behaviors. In some cases, you are able to perfectly reproduce inputs up to some point in the past, and then it drops off, or it gradually decreases. So one of the things that was already also determined by Herbert is the fact that the sum of these linear capacities, and so the integral under these curves, is always bounded by the number of states, or the number of neurons in this case, in the ESM. And the maximum can be achieved only for totally linear systems and under noiseless conditions. So no input noise, no noise in the neurons, no noise anywhere. Yeah, one important thing that I forgot to mention, and so these capacity tasks are only defined for IID input sequences, which means that your input is just white noise. And so that's a very strong restriction. That means it's very hard to use these measures if you actually are studying real life input signals. But okay, that's a theoretical framework. Now you can extend that framework, I have no time to go into that, to also include nonlinear functions of current and past inputs, and then you can have like linear functions, quadratic functions, third degree functions, and whatnot. And then you can measure a whole capacity spectrum, and you can actually study what happens if you try to trade off between a linear and a nonlinear system. So, you know, for a linear system, you can have, like, if you have 100 neurons, you can have total linear capacity of 100. If you have a nonlinear system, that capacity decreases. because other things are happening in the reservoir, nonlinear transformations. So you can measure these nonlinear transformations up to some extent, and also how they change as a function, for instance, of the input scaling or of other scaling parameters. So here I study two totally different systems. On the left is an echo state network, on the right is a simulated reaction diffusion system. And never mind, you can do these analyses on any type of system. Just make sure that you drive them with the inputs for which this capacity measure was defined. And then you can see, for example, if you increase the input scaling parameter, that the nonlinearity increases, but the total linear memory capacity decreases. So the nonlinearity here is defined as the sum of all the capacities that are not linear. Now, another thing that you see is if you add noise to the system, and so the top right plot here, if you add noise to the system, so if the signal to noise ratio gets smaller, then you see that the total useful capacity, so the sum of all the capacities that you can measure, drops off quite quickly, and drops off more quickly if you have a more nonlinear system. At the bottom, you see a similar effect appearing if you drive the system with multiple input signals, because if you look at, I don't know, the world of deep learning, and typically they want to solve high-dimensional tasks there, tasks that don't just have one input signal but multiple input signals. Well, the bad news is that reservoir computing does not work well on high-dimensional inputs, and it works even less well for more nonlinear reservoirs. So the linear boundary is the black line on the bottom right plot. So that this is how the total capacity decays per signal if you have multiple inputs, because the capacity is shared across the inputs. If you make the system nonlinear, like for instance a blue curve, then you see that it drops off really quickly, even if you only have two input signals. Because the nonlinearity mixes up all the inputs and there's all kinds of things happening. So it's really hard to extract very specific functions of individual inputs. Okay, so that was a bit of theory. Bottom line is that if you have a reservoir, there's always trade-offs. You trade off memory versus nonlinearity. You trade off the number of inputs versus nonlinearity. You trade off the number of inputs versus memory, and the total capacity versus noise robustness. So versus being able to work under poor signal-to-noise ratio conditions. So that is sort of like the general perspective, and these ideas usually also count for any physical reservoir computing system. So this is something you have to be aware of. Now there's another bit of bad news, because people sometimes think like, okay, we just make a reservoir larger and then the total capacity can be larger so we can do more things. Well, unfortunately, at least in echo state networks, because everything is connected to everything, the signals are very correlated. So making the reservoir larger and larger, at some point, you see that the performance tends to saturate. Because there's not a lot of new things being added by adding more neurons. So richness is crucial. And this is something that we can sometimes counter in physical reservoir computing, because in a physical reservoir computing, you have not everything is connected to everything. So you can have regions, you can have like some spatial structure which is driven at one side. So the response at one side will be different from the response at another side, etc. And so it's sometimes easier in physical systems to make them more inhomogeneous, and therefore to benefit more from making the system larger. Now, if you need nonlinearity and long memory and possibly also multiple inputs, so if you need more than what you can do with a single reservoir, then you're always going to be a little bit screwed. So there's only one solution there, as far as we know now. If you want to stick to strict reservoir computing, so that is typically using multiple reservoir systems. So deep ESN is one example of a multiple reservoir system organized in a very specific way. There's also been work using traditional machine learning ensemble techniques like bagging and boosting and combining multiple reservoirs possibly reservoirs with different hyperparameters, so you can get the best of both worlds. You can always make graphs of connected graphs of multiple reservoirs. And that part of research is still very much ongoing, because at this point, there's no general solution to how would you design such a multiple reservoir system, except by brute force, like they do in deep learning. By neural architecture search, you could do reservoir architecture search and just use a sledgehammer and find something good. But there's no really founded approaches to address this yet. There are some efforts, first steps, but no solution. Now there's one other issue, and so because reservoirs need to have this fading memory property, that means that by themselves they cannot exhibit persistent memory like you have in like flip-flops in digital computers. Plus that undriven reservoirs that just do nothing. So you cannot have a reservoir by itself autonomously generating a periodic pattern, for example. And these things are typically addressed by adding output feedback. And so that's what the feedback thing was in the reservoir computing in the beginning. So initially they said like, okay, let's do random output feedback. So the trained output is fed back with random weights to all the neurons. And there's a lot of theory about that already, there's already quite some things you can do with that. You can, for example, embed periodic attractors into reservoirs, and you can create reservoirs with that feedback loop in place that have multiple stable states that establish switching behavior, even and like finite state machine kind of behavior and things like that. You can also have learned feedback. You can do that, for example, by a technique called forced. You can do that with techniques from reinforcement learning. You can also use Hebbian or local learning rules. That's more like the biologically inspired approach. There's a whole like 100-page paper by Herbert about conceptors, which is another technique to embed attractors into reservoirs. So there again, there's still a lot of things going on. Research is still ongoing. You could also do sparse learning of things inside the reservoir. So in this case, you could say like, okay, let's take out a few connections and train these. In physical systems, there's also, you could actually use backpropagation. So the idea of doing backpropagation through physics was actually also first or suggested by one of my former PhD students, I don't know when, but at least more than 10 years ago, Michiel Hermans. But that is only possible if you have a reliable differentiable model of your system. So as you will see later in photonic reservoir computing, we do not have these reliable differentiable models of a single individual system. So in these cases, backpropagation is harder to use. Okay, so that is sort of the theoretical background I wanted to cover. So I don't know if there's any questions at this point.
Joni, we have some questions on the chat box. Is this a good time to discuss them, or should we leave it to the end?
No, this is kind of a break in my story, so it would be good.
Cool. I thought so, because this relates to what you've talked so far about.
Yeah.
So here,
I'm opening up the chat now. So first question I see is by someone called Leon Bello. Could you give some intuition as to about why it's better to work at the edge of instability? Well, I'm not a nonlinear dynamics person myself, but as far as I know, if you tune a nonlinear dynamical system close to that edge, that phase transition between stability and instability, then memory becomes suddenly very long. So there's a point where the memory just fades away, maybe too fast. Then there's a point where your system is chaotic and just infinitely depends on its initial conditions. And in that transient region, there is this region where the memory just becomes longer. So that's basically the more theoretical side of this. I don't know whether you guys are theoretical nonlinear dynamical people or not. Is that?
Leon is a yeah, dynamical systems person.
Okay, so then he probably knows this story better than I do.
Yeah. So I guess you're pointing to critical slowing down.
That's the term I was looking for, exactly.
I see.
Can I ask?
Yes, there's also papers about that.
There's one, Mohammed, are you asking something? Yes.
Yes, maybe it's relevant to the next section of your talk, actually, but my question is, the model that you presented is more of a derive and damp system type of model to me. And in a lot of cases in photonics or other areas, we have Hamiltonian systems that we have input, we have initial states, and we have final states. Is there studies relevant to can Hamiltonian systems be with reservoirs? My first impression is that we simply lack a fading memory in those kind of systems. But but do you have any? Yeah.
What you need to have is some way to guarantee that if you send a certain input sequence through your system, that it will respond in the same way, because otherwise your readout is not going to work. So the readout assumes it trains weights such that if you observe a certain combination of states, then your output is going to be a certain value. So if you have like a chaotic system, for example, if you depend on the initial conditions forever, then your readout is going to be different every time you send the same sequence through the system with different initial conditions. And so that's like the fundamental principle assumption of machine learning, that if you have the same input, that you will observe the same output, right? Or at least close enough similar output, because you can have noise, of course, but I'm not a physicist, so I'm not so very familiar with Hamiltonian systems, but the general answer is, if you can find a way for your system or a setup in which your system gives you that assurance, then you should be fine.
May I say a comment on this?
Yes.
I think, I mean, it depends. I mean, if you have a Hamiltonian system with dissipation, of course you can. But even if you have a Hamiltonian system, my understanding is that the readout is local and also the input is local. So in that case, you just need a system that that scrambles information in such a way that, you know, local measurements at some point cannot even tell you the information of your inputs. And so it's also doable in Hamiltonian systems.
Yes,
So,
yeah, it has to do a lot with the readout, as far as I understand.
Yeah.
Yep. We can always
This is Dan Gothier. Could I step in?
yes. Yes.
So one of the concepts that is floating around the literature now is that the reservoir needs to synchronize to the input system, to the input signal. So you can't just think of the reservoir on its own and its own dynamics. It's really a driven dynamical system.
Yeah, sure.
So as long as the reservoir synchronizes to the input signal, then it can do processing. And so as long as the Hamiltonian system could synchronize to the input, it should be a fine reservoir.
Mm-hmm.
Yeah, thank you so much.
Yeah, that's a very good point, because we often see that from dynamical theory, that people forget that we really need to talk about the properties of the system when it's driven by this particular input. So also, for example, if the system has a very low pass characteristic and you drive it with a fast input, then it will not respond and you won't see anything happening. Other way around, if the reservoir is just way too fast for the input, then it also won't work. So you have to look at the combination of the two. Otherwise, it's not gonna work.
Is it okay?
Very good points, but
question, or
there's a question in the chat box from Sadas, if maybe you could address that, Joni.
To be honest, these plots were generated more than 10 years ago. So I'm pretty sure I did the sweeps far enough to make sure that the optimum wasn't beyond the boundaries, if that is the question.
Can I ask one more question?
Yeah, sure.
So the linear memory, or I believe it's also called short-term memory. So that's something. It's again a dynamics question. That's something that you can purely basically calculate it based on the linear part of the linear part of your system. Basically, the interaction W, the W in and W out. Is that correct? Is my understanding correct?
Yeah, but in every node, there is a nonlinearity. Yeah? So the weight matrix calculates the inputs to the neuron, and then these go through the nonlinearity. So that's why you could do like a series development of the nonlinearity of the neurons and then start calculating. My experience is that doing these kinds of calculations, when the system become a little bit complicated, they get very tedious. So I'm more of an empirical person in that respect. Plus, if you go to physical, sorry, yes.
So the memory depends on the type of the nonlinearity that is in the system, because my understanding
not the total. The thing is that if you suppose that you just take like one signal coming into this nonlinearity. What comes out is a nonlinear function. So if you do series decomposition, you get a linear term plus a quadratic term plus a third degree term, etc. And these get fed back into the other neurons. So there's again transformed. So you get all kinds of nonlinear mixtures of the present and the past. Okay. So linear memory capacity says in that whole sea of mixtures, how well can you still extract the exact value of the previous and the time step before that, etc. Up to minus infinity if you want. Of course, you never get that far because it decays. So that's what linear, and all the other capacities are all these nonlinear functions. Of course, you can't measure all of them, but I have developed a way to go through that space of nonlinear functions to get the reason
I'm asking that because there is this tendency to separate a structure and dynamics, especially in complex networks context. And you are basically, my understanding is that we cannot decompose the two, and they probably each one of them have a role, but it's not that is uniquely a thing that has to do with the structure. Mm-hmm. Both are in the plane. And there is a formula for calculating the memory, because there is like an empirical formula.
So
is that a question or a remark?
I hate to interrupt. It's very interesting discussion questions I myself am interested in, but I think our memory is now fading of what your talk was. Yes. So I want to be, if you may, we have left out a generous 30-minute time for discussion. To keep things sort of flowing, I suggest we do these discussions, if you have time, Joni, in that break, if you're around. I know that you have to go.
Yeah, I'll see what I can do. If I stay around, then that means weekend work for the rest of the stuff. That's okay.
All right. Okay, I mean, we wouldn't want, we would hate to do that. So maybe we can, do this privately at a later date. There, I think a lot of questions that'd be interesting to discuss.
Okay, so let's move on to physical. So I've already given a few pointers forwards. Of course, by now there was already the reference to the bucket of water. So that is indeed the origin of the name reservoir computing, which, by the way, was also sort of launched from our team. And so Wolfgang Maas, or Netzschlager, Maas and Makram, in their paper, they tried to use this parallel of a bucket of water to explain their concept of fading memory. So like ripples in a bucket of water and they fade away. So like 1 year later, there was a team that said like, okay, let's do that in real life. Yeah, and so they built an actual bucket of water with Lego things on top, and then they had vibrations in the water according to, I think it was the spoken digits task at that point, so voice signals, and they put a camera on top and observed the ripples and showed that indeed you could classify these signals. A few years later, we discovered that these time series are actually so easy that no one should be using them anymore. Because you can actually even classify the signals just by the magnitude, by the intensity, because each of the spoken digits has a different average intensity, whatever. So that's the history of the term. And then after that, like, there was this whole cascade of all kinds of people doing all kinds of things with physical systems. And so there's a whole zoo of physical reservoir computing, like yes, we can kind of things. Hello world this, hello world there. But there are some things that you always need to keep in mind. And one is the thing that I just said before. So the total information processing capacity, linear plus nonlinear, is like bounded by the number of observed states, because these are the degrees of freedom that you extract from your system. So early on, there were people that said like, oh, but if we go to a continuous physical medium, like this, these are things from a simulated reaction diffusion system. So instead of sampling 16 points, what if we sample 64 points? What if we sample an infinite number of points? Then the bound is, of course, not the number of observed states, but the degrees of freedom of your system. So, and even worse, because it's physical system with physical measurements, so you always have signal to noise ratios on top of that. So it's like the observable number degrees of freedom of your system. So there is also a bound in physical systems, which theoreticians sometimes tend to forget. This is actually one of the core points of discussion that we had with Ingo Fischer and the delayed feedback gang in the early days of physical reservoir computing. So increasing the size of the physical system is only useful as long as you can also make your degrees of freedom increase. So increase the inherent diversity that your system can generate in transformations with respect to the inputs. Then there's another thing to think about, because if you go from echo state networks, which are discrete time and don't even know distance or space, if you go to physical systems, then you go to continuous time and continuous space by nature. So you can still have the echo states, which means that the input reverberates in the system by making cycles going somewhere else and then coming back. And there is this fading away effect, of course. If there are losses in the system, then the signal just disappears. But there can also be other effects, like interconnects. So in photonic systems, for example, some of the photonic physical reservoir, they have like discrete spaces which are nodes. And then you have interconnect, so the signal travels through an optical delay line to another node. So that interconnect has a physical delay. So that basically that means that your signal just like disappears and reappears again, untouched, unharmed, sometime later. And so that is also a memory mechanism. Of course, if you make all these delay lines 10 times longer, then you have like 10 times more memory, but like discretized, because it disappears and then comes up again, and it disappears and comes up again. And so this is like physical delay. And then the third effect, of course, is bandwidth limitations, because your physical systems typically do have bandwidth limitations. So most of the time, high frequency components will disappear, but you could also have other effects, so that you have bandpass behavior or whatnot. So there again, timescales are relevant because they have to match to your input task. So in the photonic systems, for example, having the right interconnect delay to slow down the photonics, because photonics are just way too fast for any real world tasks. And that was like one of the crucial things that we had to learn. So tuning the time scales is really crucial if you go to physical systems. So why do we do physical reservoir computing? Yeah, of course, it's fun. It's nice to play with all these systems and show that they can do something computationally, but it's also interesting because it makes you think about different views on what computation actually is beyond the digital paradigm, beyond the neuromorphic paradigms that we know of. So it's like another view on computing, natural computing, if you want. And also it connects from the neural networks perspective, it connects to many other fields where also randomness is being used. There's a whole theory behind extreme learning machines. There's also random backpropagation, all kinds of models using random projections and things like that. So there's connections. So from a scientific point, it's kind of a cool field to be in. The other thing is that it's far less crowded than, for example, the deep learning field. So that's also nice. And from an engineering perspective, because we are an engineering group, then you're looking for benefits. So why is it useful to do it like that? So in photonics, for example, it's often going to be speed. In spiking applications, it's speed or power. So there's benefits there. Sometimes it's also useful to say, like, okay, let's just stay in the analog domain. Let's not force our analog signals into a digital harness and then compute and then force them back, because maybe you're even going to lose some stuff along the way. In robotics, the motivation is very often that you can just exploit the computations that are already being done by your body. So if the body already does some transformations that are useful for control of locomotion, for example, then you can just as well use them and do less computations yourself. And the last thing is, of course, easier learning, because you're basically just doing linear regression, which is a lot easier than more complex algorithms. So these are all kinds of motivations for why you, motivations at least that have been used already in literature for why you want to do reservoir computing, physical reservoir computing. Now, as I said, there's a whole zoo of them. The most pronounced families at this point, I think, are like photonic is one of the oldest for sure. Mechanical systems, biological systems, or biologically inspired, because of course you also have spiking neural networks that are electrical implementations or simulations, even DNA, plants, organisms, and some electronic approaches. There's others, I'm sure, and I'm definitely gonna forget people, but that's just like the largest clusters that I'm aware of. I've also put two links to quite recent review papers. The first one is mostly a very extensive enumeration of many different techniques. The second one is less enumerative and also tries to put in some insight, some understanding, and some links to the theory of reservoir computing. So if you want to read on more, that's a good starting point. Okay, now I'm going to just give a few highlights from my own experience, which is mostly in photonic and mechanical systems. So photonic reservoirs, there's like two very different branches. Our work has mostly been in the what we call parallel photonic reservoirs. So we started with simulations where we had a grid of silicon amplifiers, which were connected by optical delay lines. So there's the delay line story that I was referring to. But very soon, so when sweeping these hyperparameters for linear versus nonlinear, Christophe van Doorne found that actually the system worked just as well in a very linear regime. So that's when we decided, so okay, making these optical amplifiers on chip is going to be hard anyway and very power hungry. So let's just throw them out. So the photonic reservoirs we're working with now are just linear reservoirs, and actually just the nonlinearity at the photodetector. So when you observe the photonic signals and transfer them to electrical domain, that nonlinearity by itself is enough. So the reservoir basically just provides the memory. So you have like the memory, which is spread out. Then you do the nonlinear detection, which is quadratic almost. And then you do the readout. That was the first work. Now we're actually doing the readouts in the photonic, in the optical domain. So we're working with coherent systems. That means that you have to tune both the phase and the magnitude, and then take complex valued linear combination before one photodetector, because these photodetectors, high bandwidth photodetectors, are quite expensive. And so that's why we shifted the linear combination into the optical domain. And there the rationale, of course, is telecom applications where the signals are optical anyway, and where you hope to achieve low power and high bandwidth solutions for typical telecom tasks. So here you see a picture. This is simulated from nonlinear distortion compensation. So the left thing basically has no eyes, and on the right, at least, you see some eyes appearing. These are slightly older results. These are somewhat more recent results. I haven't immediately found the link, the URL to the publication, but here it was actually shown that using reservoir computing, you can outperform traditional electronic solutions for nonlinear distortion compensation. And here, one nice catch was that if we, so typically they try to optimize the photodetector to have very good behavior, to have a very nice linear part of a regime. And actually for us, having a bad performing non-linear photodetector was actually better for solving our task. So a bad means a cheaper photodetector. Okay, then the second family, which is a delayed feedback reservoir computing, that was also started around the same point actually quite soon after the buckets, but the first publications were a bit later. So there you only have one nonlinear node. And so the input is mixed with something that comes back to a delay line and then sent back into that delay line. And the input signal is actually much slower than the time of that delay line. So the input signal is modulated by periodic mask, so that actually the same input value is sent into that nonlinear node with many different magnitudes. So you get all these different mixings, and then there's many variants where they make the delay line slightly shorter or slightly longer than the input mask, and there's a whole zoo of these things around there as well. But the bottom line is that then you also read that out multiple times across the masking period, and that is roughly equivalent to having multiple neurons in space. So it's actually sort of a time multiplexed multi-node reservoir, if you want. So again, there's many implementations. Originally, they were very bulky with this very large spools of optical fiber on a table, but now these things are also moving to integrated solutions. So yeah, that's the other part. I don't have any results there because there's just too many of them, so I can't show any. But that's a very large body of work on photonic reservoir computing. Okay, then the other part, so mechanical, actually, yeah, let's skip the slide. So mechanical systems as reservoirs. So this whole story started, I think, with the paper from Helmut Hauser on simulated mass spring damper systems. So you have masses connected by springs, and there's dampers in there as well. So if you touch this thing, it will start oscillating and vibrating and doing stuff, and due to the dampers, it's still fading. And so there's a whole theoretical paper about that. There is also like the first time where they say like, okay, you could also have a linear system and a nonlinear readout. If you have a nonlinear readout that is a universal approximator, say a perceptron with one hidden layer, for example. And if you have a reservoir that is universal in the sense that it can have infinite memory capacity, if you make it infinitely large, linear, then you can still have task universality. So that's some of the theory that's in that paper. And then based on that, there was lots of work emerging on physical mechanical systems, some with quite recent with mechanical oscillators is actually quite related to the original Hauser work. On the top left, the bottom left, you see a tensegrity robot. So that's a robot with sticks connected by strings with fibers, and these strings are also being actuated. So the whole thing kind of wobbles. And then using reservoir computing approach on that body, you can actually make it move or draw letters in the air or things like that. And on the bottom right, you see the work by Kohei Nakajima et al., which started with this octopus arm thing. So that's compliant and soft robotics. So Helmut is now also mostly in soft robotics and reservoirs. And so there you use the robot body as a reservoir to either do control, but it can also do, as like the tensegrity robot could also do underground classification. So classify which type of underground it is moving on. Yeah, or the octopus arm as well. It can touch things and then try to decide what it's touching. So that's also one of the things I forgot to mention. One of the very nice things with reservoir computing, and that with a single reservoir, by training different readouts, you can actually do multiple tasks on the same reservoir driven with the same input. So that's also a nice thing with reservoir computing. Some of the work we have been done on robotics. So we've done quite a lot on quadruped robots. On the left, you see Onchilla, which is now in a care home for old robots. At the bottom right is the more recent version of our quadruped robot. This was done in the framework of the Human Brain Project. And on the top right, you see a simulated mass spring damper robot, but which is organized a little bit like some sort of worm. So you can actually teach it to crawl and to move forward. So we have 3 different papers. What is common here is that in all these cases, we found that the body itself as a reservoir was not enough to solve the tasks. So you needed more. So in the cases at the top right and at the top right, we just added a delay buffer because the body did not have enough memory. So it provided the nonlinearity, but not the memory. At the left, we actually did an exploration. So there's an extreme learning machine in there. So something that provides extra nonlinearity and a delay buffer. And we explore like, okay, what do you actually need? Do you need memory? Do you need linearity? How do these things trade off? And at the right, we actually used additional reservoirs of spiking neurons to sort of be the brain that works together with the body, but both were treated as reservoirs to do quadruped locomotion. And so again, there's all kinds of things going on. And so all of this was teacher-forced closed loop training approaches. And this is a very recent one that I just plucked out of literature. So these are like origami robots. And so they're like sheets of, I don't know what kind of material, and they are folded. And then they also have like mechanical properties. So they have spring-like properties. They tend to want to fall back to their normal shape. So you can also stretch them or stimulate them in some way and use them as a reservoir. For example, again, to teach them to crawl or to locomote or things like that. So this is a pretty recent paper. So this thing is still going on. Okay, so these are some of the things, thoughts, lessons that I have learned. So what is physical reservoir computing? Basically, it's in the engineering sense, a way to exploit the computing that naturally happens in physical systems by just putting linear regression on top and sometimes some other tricks. It's also a new way of thinking. Well, new, it's 20 years old, but a recent way of thinking about general purpose computing with analog dynamical systems. And then, of course, when you move to physical reservoir computing, it's important to analyze, okay, this system is not a general purpose system. So what are the properties of this system? Does it have a lot of memory? Does it have a lot of nonlinearity? Am I capable of tuning between these two? Yes or no? What are the time scales? So first characterize the system that you have. And some limitations. And so for any system I've seen thus far, the performance does saturate if you make it larger. So there will be some point where you need more complexity than a reservoir can give you. They also, all of them still have trouble to handle many inputs. They're all sensitive to noise. The linear ones are least sensitive. The more nonlinear, the more sensitive to noise. And unfortunately, there's still a lack of systematic techniques to go beyond single reservoir systems to go to multiple reservoir systems. Okay, that's what I wanted to tell you. And now I'm going to try and find my Zoom meeting again to answer any questions you might still have.
Okay, Joni, thank you very much. This was a wonderful introductory talk. I don't know,
With the
on
time
behalf of the 40 people here. So we are terribly behind. I would love to take more questions that I see on the chat box here, but what I suggest is we move on. And Joni, if before you leave, you could maybe answer those questions on the chat box, at least directly to, responding to the questions that remain. That'd be great. Would that be okay?
I'm seeing a few that I'm not, if they go too deep into the nonlinear dynamical systems, then I'll have to, the
Yes.
synchronization thing, for example, I will leave that to other people. I could try and come back in half an hour or so, for 45 minutes, to see if there's any more questions popping up
Okay, wonderful.
during the break.
I
But I'll
suspect
see what I can answer.
the break is shrinking fast anyway, so we may have no break left at the end. So, okay, but this was this is the kind of discussion we wanted to encourage in this symposium. I think there are many questions, which is a testament to the youth and vigor of the field. So, thank you very much again, Joni.
You're welcome.